Okay, so welcome back to the Python GPU class. So I'm Alice Faure. I'm a research engineer in scientific computing. And for the next hour, we're going to talk about CuPyNumeric and how we can use it on our GPU. So it's going to be quite straightforward, the modification of the grayscale implementation that we're going to make, because the goal of CuPyNumeric is to port your code from CPU to GPU almost with zero modifications. If you watched the webinar on Python GPU, I talked a bit more in detail about it, but CuPyNumeric is still in development. It's in its beta phase. So there are a lot of bugs. There are a lot of things that are not yet very optimized. So we're going to test it. We're going to see if we go a bit faster with it. Maybe you noticed that sometimes we use the term CuNumeric because it just changed its name last year, I think, or 2 years ago. I think it was last year. So now it's called CuPyNumeric, but it's the same library as CuNumeric. And so it's a NVIDIA library. So I think you can only use it with NVIDIA GPUs. Okay, so what we're going to do here, I opened the tutorial, so it's the number 2, the .md or the tutorial files, and then we're going to use some Python scripts, and we're going to optimize them. So normally, if you tested your Python GPU setup, you should be able to import CuPyNumeric. If you have some trouble, we can check it. If you are on must, I wrote a little install procedures that maybe you saw here. So if you are on your own laptop, you can follow this procedure. If you want to use Docker, but I don't really recommend it, you can follow this procedure. On the must cluster, we're going to see together how to submit jobs. Because if you want to use the GPU on the must cluster, I don't think we can do 20 interactive sessions at the same time. So we're going to submit jobs using the submission scripts we prepared. And if you are on a different cluster, you should have contacted the administrator of your satellite site, because they should have told you how to submit jobs on their cluster, because it's dependent on the job scheduler. Okay, so let's take a look at the submission files that we wrote for the must cluster. But if you are running on a different cluster, you will have to modify them a little bit. So normally you should have cloned the Git repository. So let's go on the cluster directory. So you have 3 scripts here that we're going to use to run our codes on the GPU on must. So the first one will run the apptainer. So we have a dedicated apptainer image that is called GPU and latest.save. Okay, so what you need to adapt here in this file is just your username. Yes, so the path in which you cloned your Git repository. So it's maybe your username, or maybe it's SSH and the number you were attributed. So you're going to have to adapt this file, the path here, but then you should run the container here. So this script will run this apptainer container. And it will run also a script that we put inside the apptainer container. So let's check this script. So this you're going to have to modify every time that you run a different Python script. So, well, here this version I put on the GitLab is running grayscale Jack solutions, but we're going to modify it to run CuPyNumeric solutions. And what you have to adapt are also the path here. So here the prefix, you also have to put the directory in which you clone the GitLab. And I think it should be all. Okay, so let's do that together. So first we're going to take, no, yeah, there is another script I forgot to present, is the submission script for the job scheduler. So it's very straightforward. What you just have to do is write your email, and that's all. And this script will request an A100 GPU. Yes, and that's all. And we'll run this obtainer that we prepared. Okay, so let's do this. So I'm on the lab cluster. No, I have to reconnect. Sorry, I'll do that. Okay, in the meantime, what you can do is take the CuPyNumeric Python script. So here you can click on this link, but it's also in the no, it's not, sorry. So don't click on the link, it's in the script directory. So you take Grayscale CuPyNumeric, it's the same script we use for the Python CPU class. So we put all the functions that we saw already, and you're going to have to optimize it with the with CuPyNumeric. So here you import it, and then you're going to have to modify the function so that you respect the best practices of CuPyNumeric. So I put a link of the best practices. Normally it should work. So if I go back to my class here, okay. So you just have to import CuPyNumeric and follow the best practices here. So if you click, they give you the best practices. And so try to modify the code to follow them. There should not be a lot of things to do. It should be quite straightforward. Try to run it using all the scripts that we provide on your cluster. And don't hesitate to ask questions if you had some problems. I'm going to run one script live so that you can see what it gives me. But if you want to do it on your own, feel free to do it. Okay, so I'm on the lab cluster, and what you have to do if you're on the lab cluster, you go to lab data formation here, and I think what you have to do is create a directory in the Grayscale GPU, probably. Yes. So here you can see a lot of directories, so you can create your own. Clone the Grayscale Python class. And then, so I'm going to go to my own directory. Okay, so I'll just run git pull. All right, so I'm going to the GPU cluster directory. I'm going to have to modify the obtainer script here. So, well, for me it should be good, but you're going to have to modify this prefix here. I'm going to check. Okay, so I'm running CuPyNumeric solution. So you should check that you're running the right script. So I'm just running CuPyNumeric, and I want to run it from the scripts directory. Okay. Here I put my mail. Okay. So to submit it, you have to do condor submit and the Grayscale Python.submit file. Okay. And then condor q. And so here I can see my job. Did you manage to submit a job to check on the mass cluster? Okay. On the satellite site, it's slow? Yeah, it's normal because you're a lot, I guess. But the script, okay, the script itself is very slow, the CuPyNumeric script, yes. 300,000? Did you integrate the last changes? Did you do git pull? Because I think it's milliseconds. Yes. Yeah, there was a problem between milliseconds and seconds that I changed yesterday. But still, you can just cancel your job so that you don't run forever. Okay. So try to optimize the Grace Code CuPyNumeric script on your side, and I will help you if you want. Okay, so the import is already done, but then you have to do. I think the most important one is to return the where is it? Use output arguments to reduce memory allocation. I think it's this one that you have to put in most functions, but that's all, I guess. Okay, try to do it, and then we'll correct in maybe 15 minutes. So normally you should have here divided by 1,000 if you integrated the last changes. But yeah, okay, maybe the time that you get is in milliseconds and not seconds. So, but just check with your. I mean, if you have like 300 seconds, it's okay. It should run like that. If you have 300,000 seconds, it means that it's in milliseconds and not in seconds. So I'm going to try to cancel my job because I don't want it to run forever. So normally the command should be this, condor_rm. Can you see my screen, or do you want me to put it? Maybe I'm going to zoom. Okay, and then the ID of my job that I got by doing condor q. Okay, and then if I redo condor q to check the queue, I have no jobs running. Perfect. Okay, so to cancel your job, you can do condor_rm and the ID of your job. Okay, so just to clarify, this script here is the script that we wrote in the Jupyter notebook last week. It's exactly the same. I just changed the import CuPyNumeric here. But it's exactly the same. And we put all the functions that we wrote together. And the goal of CuPyNumeric is to be able to run the same code on the CPU or on the GPU, depending on how you run your code. So if you want to run only on a CPU, you just have to specify it on your Legate. Let me take it. Legate instruction. So it's here. Okay. So here with Legate, you can choose whether you run on CPU or GPU. So if you ask for one GPU, it's going to run on a GPU. So you can try maybe to write this legate command in the script inside Container. So here for the moment I put Python, but if you put Legate, it should work also. Python, I guess it would run on a CPU if you don't specify anything. So I'll ask for one. Plus one. And so normally you should be able to run exactly the same script on CPU or on GPU. And what we're going to do in the last remaining half an hour is to just respect the best practices of CuPyNumeric to see if we can improve a little bit the runtime. Okay.
instead of obtain or run, now what was the command?
The obtain or run?
No, you remove Python and you put what you did.
I put this legate command that I put in the tutorial. You just follow the tutorial steps. So you import CuPyNumeric as NP, but this is already done. And then to execute it, you have to run it with this command. And you can change all the arguments here. So here I asked for 1 GPU, so I just put 1 GPU on my command line. This is how you can choose on which architecture you're going to run. If you remove the 2000, it depends on the cluster you are on. I know on my lab cluster it doesn't work because it's mandatory to specify the memory, but on the most cluster it works. So.
How do we select how much memory we want?
But I guess you have to check the memory of the GPU, but usually it's not that high. I put this because on my cluster it works, but maybe on must it should be adapted. All right, so let's take a look at the differences between the NumPy implementation we made last week and the CuPyNumeric implementation we can do. So other than importing CuPyNumeric, we can try to follow some best practices that they specify in the documentation. So you have two versions of the script, the one that you are supposed to adapt. Here, Grace Code CuPyNumeric in the scripts directory. And let's take a look at the solution, which is in the solutions directory. Okay. So CuPyNumeric is not very fast, so we tried a bunch of Laplacians. So we tried the Laplacian convolve here. That is from the NumPy library, but also they adapted it to CuPyNumeric, so you can test it. It should be a bit faster than the Laplacian NumPy that we made. So for the Laplacian NumPy, we did not change anything. One of you pointed out to me that the NumPy.zeros here that we do does a float 64 matrix, and this is not what we want. So I didn't include it in the solutions yet, but if you want to include it, well, you should. So instead of using zeros, use the zeros-like function to define an array that is of the same type as the one we want to use. So it's float 32 that we want to use in this class. So yeah, you should definitely put that here. Other than that, what you can do as a modification is probably here on the Grace Code these steps. They specify in the best practices that you have to use output arguments to reduce memory allocation. So instead of doing u equals u plus, etc., we do np.add u, and we put u in the out. So this is what we do here, np.add, so CuPyNumeric.add u, and then the member of the equation, and then we return it by out. Okay, so this is, I guess, the principal change you have to make. Yeah, I'm not sure we did some other changes actually. Okay, so you can try both versions and see which one runs faster, but unfortunately, I didn't manage to make changes in a way that CuPyNumeric would run really fast. So the benchmarks we made, the CuPyNumeric solution was like 10 times slower than the JAX and CuPy and PyTorch solutions. I guess it's because it's still in development. Okay, so if you want to try to run this solution here, you just maybe you should modify here the np zeros and put it zeros like here, and then you can run it as is. So let's try to do it. Unfortunately, I think my jobs are idle because we're a lot of us are computing, so we have to wait a little bit. Okay, so here I also put dtype equals np.float32 in this images array. So here, instead of running my script that I worked on, I'm running the solutions one. And it should be straightforward. So I'll give you a few minutes to do that yourself if you need it, and then well, I guess we can compare the runtimes we have. So we've done a little benchmark array here. So with the convolve function of the NumPy library, we run on a A100 GPU on 128 seconds. And as you can see, it's much slower than the other libraries. So normally you should have some runtimes of 100 to 300 seconds if you run it yourself. Okay, so take a few minutes to run this solution script, and then we will conclude this this tutorial. So do not hesitate to ask questions, satellite sites, on the Discord and in the room, and I can help you with your implementation. If you have some errors about GPU reservation or allocation, it's maybe because you run your script with Python instead of Legate. So maybe I should have explained it more in detail, but if you want to run on your GPU, you have to use the Legate driver here. You cannot just put Python grayscale CuPyNumeric. I mean, I'm not sure it will work. If you want to be sure that you run on a GPU, you have to specify this command here. Instead of doing Python grayscale CuPyNumeric.py, you do Legate, you specify the resources you want, the memory you want here. Here is the memory of the GPU that you want to allocate, and your Python script. So this is the proper way to run a CuPyNumeric script. Okay, so I'm still in the queue, unfortunately. I don't really know why. I think a lot of you have the same problem, so maybe we'll check that at the lunch break. But I think we can stop for now. A few of you have managed to run on the mass cluster, and I think it was 300 seconds or something like that. So yeah, this was the first test of CuPyNumeric. Maybe in the following years it's going to get faster, but for the moment this is what we have. For this afternoon, we're going to compute with JAX. So for this, we're going to use the same code we have for the CPU class, and then we will optimize it with JAX. Okay. So, but I suggest we stop here since the queue is not going to move, I guess. If you have some questions, ask them on the Discord. And if you have some problems setting up the GPU environment, do not hesitate. For this afternoon, it's going to be important to run with JAX also. Okay, thank you for your attention.